Right, thank you, Jachi, for the introduction. My name is Tina. I work for KeepTruckin. You might be wondering what trucking has to do with machine learning. Trucking is a $800 billion industry. In the United States, 70% of auto products are moved by a truck to their destination. But not only is trucking a huge part of our economy and the supply chain, we're also sharing our roads with them. Even though trucks only account for 10% of the miles driven, they are involved in 74% of all the fatal passenger vehicle accidents. So here at KT, we build tools to improve the safety and efficiency of businesses with not only trucks, but all kinds of vehicles. We have a vehicle gateway device to handle compliance and an asset gateway device to track locations. But today we're gonna focus on this AI dashcam in the middle, which we built with a suite of safety products with machine learning. Videos are sometimes the best tool to identify unsafe driving behaviors and exonerate drivers when they are being wrongfully accused for an accident. Here in this example, we have an inward-facing video, of which we build models such as cell phone usage or safety belts. With the road-facing videos, we can two of the most important models we built are lane detection, vehicle detection. And on top of these, we build other models like close following, whether we're maintaining a safety, a safe following distance with the vehicle in front of us or not. These annotations greatly reduces the manual labor needed for fleet managers to inspect these videos. And imagine you're a fleet manager for 5 trucks, and these trucks are driven by multiple drivers per shift, maybe for 20 hours every day. So every day you get 100 hours of raw video footages for these videos, and it's impossible for a human to manually inspect all of these for unsafe behaviors. And these safety features is really, really important for our customers because accidents are really expensive, especially when the truck is involved. Sometimes even one accident can put our customer out of business. So with these annotations, it's really clear what is happening and what they should pay attention to. Every time they see this pink exclamation mark, it just means we are following this vehicle too closely. And this is just one example of our many products. We are a leader in the fleet management space. Over 1 million drivers and 100,000 companies across every industry use our platform to power their operations, prevent accidents, and reduce costs. And machine learning is a very important piece of that solution. So today, I would like to talk to you about how we deployed our ML models on Kubernetes, and we'll go over 4 things together. How do you serve your model? What infrastructure to deploy that model server on? How to scale your applications according to traffic? And some things to consider when you're monitoring it in production. I see some familiar faces in the audience. This is who I'm assuming is in the room today. Drop a 1 in the chat if you're a ML researcher who trains ML models and want to understand more about how to productionize them. Drop a 2 in the chat if you're more on the engineering side, maybe already a user of Kubernetes. If neither of that applied to you, let me know in the chat too, what's your background and what might be the most helpful thing for you today. But I'm gonna go ahead and assume that people here have a general understanding of machine learning, containers, and basics of cloud computing. Okay, so imagine you're a computer vision researcher and have successfully trained the lane detection, vehicle detection model we just saw. You're happy with your accuracy and you want to use them in production. So first, you need to save your model results somehow. And when I say save, what I'm actually saying is saving the weights and parameters you just trained. We don't need to save all your Python code, how you cleaned up your data, what number of iterations, learning rate, all the hyperparameters you ended up choosing, because you don't need them to make a prediction. Take this very simple linear regression model, for example. When you're saving this model, you only need to save this 0.2x plus 5 function. And when a new data point comes in production, what you will need to do is to just multiply it by 0.2 and add 5 and return that prediction. Our computer vision model is a lot more complicated, but the idea is the same. you'll just be saving all these weights in each of this layer and this entire neural network architecture. But essentially, you're still just saving a mathematical formula with weights that you just trained. And we'll get a new data point, just like the linear regression example. You do the math, the whole forward propagation, and you can return that result as your prediction. So all ML frameworks have this model saving functionality. It's usually as simple as calling some model.save. If you learn ML in school, this is probably where you stop. You learn about how the models work. You train the model in a notebook. You know that you can save it somewhere locally, and you can load it later, maybe also in a notebook and make predictions. But how do you actually use this in real time? There's no notebook in production, and there's no you to be there to manually trigger this inference. How you apply your model after you've trained it, it's called model serving. There are a lot of different frameworks you can use. We chose TensorFlow serving because one, our models are trained in TensorFlow, and also TensorFlow serving is pretty powerful and easy to use, open source by Google, and Google also widely uses it internally as well. All you need with TensorFlow serving is to create a container with this TensorFlow serving image as the base image and copy in the model artifacts you just saved. And this base image will handle loading the model and forward the incoming request to your model to do the math and return that result. And this is basically how we automate the prediction step. It's actually pretty straightforward. So you will build this image, push it to a registry. You can deploy it anywhere because it's a container. You can deploy it locally, and most likely somewhere in the cloud. We deploy this on our Kubernetes cluster, which is on AWS. I will talk about that very soon in the next section. For now, assume it's running somewhere, just like a web server. This is your model server, and you'll have some client that will be sending the inference requests to it, and you will return some prediction results back. And you can hit this endpoint either via REST or a gRPC. REST looks a little simpler, but sometimes gRPC, people argue that it's a little faster because the network is more network efficient and because the payload is smaller, but either would do. So now you package your model in a container with TensorFlow serving, and you can accept either REST or gRPC inference requests. And now let's look at how and where will you run your container. And one way is you can just start EC2 instance. You can download the container there locally, host the endpoint with some Docker run command. But what if your traffic is a lot more than what one container can handle? Manually manage dozens or even hundreds of containers is not scalable at all. What if you create a newer and better version of your model? Imagine how much work it would be to have to SSH into all these nodes and run a Docker pull command. So here's where a container orchestration tool like Kubernetes come into play. Kubernetes greatly reduces the operational complexity by automating a lot of things like scheduling, resource allocation, scaling, health monitoring, networking. The list goes on and on. And I'm not going to go into details about how Kubernetes work today, but the main takeaway here should be this distributed container infrastructure can get pretty dynamic and complex, and we need help with managing it. Kubernetes is one of the leading solutions in the industry right now. It's open source, very well adopted by many companies and supported by a big community. Specifically, our use case, we created a Kubernetes deployment and a service. So both deployment and service are abstractions in Kubernetes. Just like when you sort the list in Python, you run list.sort. You're not concerned with which sorting algorithm Python actually implemented. That is a level of abstraction. Here, deployment is in charge of keeping the pods running in a cluster. For example, one node accidentally died, and you don't have to manually go in there and create a new one. Your Kubernetes deployment will help you do that automatically. Similarly, a service is in charge of granting network access to your pods and let you send your gRPC requests to a stable IP address. That's not going to change even though pods are terminated and created dynamically all the time. These abstractions help handling the lower level objects, so you don't have to. We deployed our lane detection and vehicle detection model behind a TensorFlow serving endpoint on Kubernetes as a deployment with service to so that we can make gRPC requests from our client. And this is a diagram of that architecture. So with this application pod here, it pulls videos from this queue and does some pre-processing, makes the gRPC requests in parallel to these two models and gets the result back, draws the overlays on top of our original video and saves that to a S3 bucket. We then applied some Kubernetes magic here and separated this application, this client worker, into a separate namespace from the model endpoints. So the application worker is living in a CPU namespace, which only allows CPU instances, and the model endpoints are living in a namespace that only allows GPU instances. By splitting the application worker and the inference endpoints across namespaces like this, we maximize our GPU utilization because the only computation that is happening on the GPU instances are the deep learning inferencing. And Kubernetes let us deploy different services and manage the type of instances and resources we want very easily. Here we did that with the help of namespaces. So now you have your actual models running behind TensorFlow serving endpoint. You can send videos to it and you will get the overlay result back. Your whole system is actually already up and running end to end. But this is production and traffic can change. So you may want to start thinking about how to scale your system up and down according to traffic. For us, we mostly serve customers in North America, so our traffic varies a lot depending on the time of the day. 70% of our videos come between 4 a.m. and 1 p.m. PST. And Kubernetes have a lot of tools to help you scale your applications. So first, you can manually do that. This is an example of me setting this lane detection deployment to have 2 replicas with 2 pods. Most likely you'll want to automate this so your system dynamically adjusts to demand. And this demand is usually represented as some metrics with a threshold. Well, here are 3 kinds of metrics Kubernetes support as of today. First, you can use some per pod resource metric. This being either CPU or memory usage. And this example here just tells Kubernetes that if on average your pods are consuming more than 50% of their CPU requests, scale up. Second, you can use what Kubernetes call custom metric. Basically means a metric that's on a node or pod that is not the CPU or memory, or it can be on the deployment level, some metrics average across all the pods in the deployment. This example here, we are telling Kubernetes to scale up if on average, each pod is serving more than 1,000 packets per second. Other examples for custom metrics can be the queries per second, requests per second, writes per second, network performances. Third, you can use some external metrics. External means the metric is outside of this Kubernetes deployment. For example, here we are saying that if on average, the number of messages within a queue is more than 30, we want to scale up. This queue, this is external because the queue is not part of your Kubernetes deployment, but the number of messages in the queue represents your workload. So you can use it as a auto-scaling metric. And these metrics from external application need to be exported some way so that Kubernetes can access it. So now you may want to ask me, so which one of these 3 did you choose? We actually did not choose any of these 3 options, but we went ahead with some automated version of this manual way. And let me explain why. So we initially tried to scale the application worker on memory usage or CPU usage with this first kind of metric, but this did not work very well. And that is because the memory and CPU footprint of an application worker varies a lot over the life cycle of processing a video, which led to erratic changes in the number of pods. Basically, system level metrics are a little too volatile for us. And it seems that maybe we can try this third kind of metric. We do have a queue, so maybe we can scale our application based on the number of messages in our queue. This sounded pretty good, but it didn't work either because on average, our GPU node takes 5 to 7 minutes to create, and that is not acceptable for our SLA. This is just the unfortunate nature of auto-scaling. It is always going to be responsive. Your system will only scale up when it's already overloaded. But the scaling up in our case is too slow. So we need to be more proactive and sometimes over-provisioning a little bit. So we found this open source tool called Kubernetes Scheduled Scaler that allows us to hard code the number of pods we want according to a cron schedule. And it will run set the specific number of pods command for us. And creating a set schedule is a great choice for us because we are blessed with very periodic workload, as you can see in this chart. So we calculated the average number of videos for each hour from our history data, and then calculate how many application pods and model pods we need. So the gray line here just shows like the traffic, and the pink is the number of pods corresponding to the traffic pattern. This has been working pretty well so far. The only drawback is that we do have to go back and regularly check updated numbers when our traffic pattern changes. Now you have your deployment ready, you're confident that it will handle the traffic well with a reasonable scaling strategy. There are quite a few things we should monitor for production systems to make sure that our service is healthy. First, some metrics that you can look at. CPU and memory usage, very important with Kubernetes. For any pod, you can request a desired size with the upper limit. So you can specify your pod to have at least 4 gigabytes of memory, but no more than 8. If your pod is too small and your container goes past its memory limit, the pod will be terminated. And if your pod starts hitting your CPU limits, Kubernetes will start to throttle your container. And if your pod is too big, then you're wasting resources and money. So keeping an eye on your actual CPU and memory usage in production will help you understand whether your resources are being efficiently used. At the service level, you'll want to understand your throughput and latency to make sure that you're meeting your SLA. And for us, this is even more important because remember, we are hard coding our scaling schedule based off of this assumption that our traffic pattern stays the same. So we need to regularly go back and verify this assumption. Lastly, you'll want to check your model health. Just because you trained it very well offline doesn't necessarily mean that it will perform well in production. Take our, again, lane detection, vehicle detection model, for example. Maybe we thought our models are great and deployed them, but then we realized that they're not performing very well when the videos are taken when it's raining in production. And this could be caused by us not having enough raining videos in the training set. So this requires us to compare this prediction from production with some ground truth. With our computer vision models, we actually have a team of human annotators reviewing our upload videos and give us feedback on the quality of our overlays. You might get your ground truth a little bit differently. It might be a delayed metric like ours, but it's very important to have the sanity check step to track your model health. ML is a continuous process. You deploy it, you get some production data, analyze it, and kind of just iterate on it. That is for metrics within a live system, things can go wrong at any time. Even Facebook can go down for hours, as we saw last week. If you have just one big node that runs your application, it's fairly easy to debug. But when you have a microservice architecture like ours that have a lot of moving pieces communicating with each other, distributed across instances and moves around as needed, a lot more things can go wrong and it can get a lot harder to debug. So you should set up first alerts on metrics you care about, the metrics that we saw from the last slide, maybe other things that are important. For example, we have alerts for the number of messages in our queue, alerts on if the scheduler didn't set the pods correctly every hour. Log aggregation is also very important because containers are ephemeral, meaning if a container dies, everything inside of it is gone. You can't SSH into it and look at the logs anymore. So you should set up log aggregations. You can debug your issue. You can also like alert on log errors here. Instrumenting your deployment with tracing can be also very helpful. Tracing basically visualizes the full lifespan of requests from end to end, so you know exactly how long each part of the code is taking, and some dependencies between services. So with tracing like this, you no longer have to write all the start equals time to time, end equals time to time, and elapsed time equals end minus start, like round that to an integer number. This visibility really helps you optimize application performances. And here at KT, we use Datadog for this monitoring. Some of your companies may use ELK or Prometheus. Doesn't really matter which tool you use. These are just some things that we think are pretty important to look at. All right, to recap, we talked about serving your model as a TensorFlow serving endpoint, deploying that endpoint on Kubernetes, calling the system properly, scaling the system properly according to traffic, and set up monitoring so we can troubleshoot when things go wrong. And all the things we just talked about is what's behind this Fleet Manager dashboard screenshot. In the middle, you can see this overlaid video our model produced. At the bottom, we have some speed information. There's some more sensor data that's cropped out because of the size of the slide. On the right, we see that this video is categorized as close following and heartbreak event. And our annotators added even more context tags. Maybe we had a risky driver, maybe not in this frame, but some other frame. The time of the day is dawn, dusk, maybe constricted lane, also in a later frame as well. So by leveraging ML, we provide snapshots of valuable data and alert fleet managers to pay attention to important things. Before technologies like ours existed, they have to watch hours and hours of footage. And if you think driving for a long time can cause fatigue, just imagine how much more boring it is to just watch videos of other people driving. Not only do we enhance these videos, we're also combining them with other sensor data that may not necessarily be available to the human eye, like the speed information here. So in short, we use Kubernetes to help us build AI products to help fleet managers execute their job with a lot more information in less time. And that is all I have for the presentation. I want to thank Women Who Code for inviting me today. Both trucking and tech are traditionally very male-dominated industries. I'm really happy to be here representing KeepTruckin. We're also in a shortage of many things in this country right now. I just moved into my new apartment and I wanted to buy a sofa, and every place that I visited told me that I have to wait for some time next year to get it. Transportation provides critical infrastructure for our country, and it's our hope at KT that we can make it safer, more effective, and more diverse. Not only will it help build a strong economy, but also safer infrastructure for all of us. With that, I'd like to open the floor to any questions you have. Thank you.
Awesome. Yeah, we already have a couple in the Q&A, and if attendees have additional questions, feel free to put them in the chat or Q&A. I see that, Ashley, you've answered a couple. I think the first one was, do KT customers who purchase AI dash cams need to understand containerization coding to get the value from these cameras? And Ashley, your response was they do not. If the attendee has follow-ups, feel free to put that in the chat. Next one from Lane Crawley is, do KT engineers set this up? And we were wondering, I guess, what is this that you're referring to? So if you would like to elaborate in the chat, we'll come back to you on that question. I'm going to go with this question from Amir. Hi, have you guys tried deploying the ML models using Kubeflow? It's also using Kubernetes under the hood. If yes, can you please explain a little bit about it? Thanks.
All right, thank you for your question, Amir. We do use Kubeflow here for model training at KeepTruckin. We do not use KF serving. I think there was no reason for us to move away from TensorFlow serving as of now. It's working pretty well for all the use cases that we care about, but might be an interesting thing to explore. Curious, why are you asking those? Is that something you have tried? Do you have a preference? Do you know what's something that you like about Kubeflow that is not available for TensorFlow serving? Maybe you can also learn from your experience. I think Lane clarified his question. Who sets up the containerization we're seeing? Me and my coworkers. Who sets up this allocation of resources? We have a team of great SREs and platform engineers. I see some of them in the audience right now. They help us manage our Kubernetes clusters.
And I think another question, does the model predict at runtime?
Yes. The answer is yes. So we get videos sent to our queue, and then we keep pulling from this queue. We return the videos after the inference is done. And basically it shows up like this dashboard like this for people.
Very cool.
Said, and they have used Kubeflow with TFX pipeline.
Cool. Any other questions from the audience?
From a DevOps point of view, have you guys deal with any bottleneck at the time of you deploying your ML models? I'm not too sure what bottleneck means here. I guess we do want to scale our applications accordingly with the schedule that we have. That is probably the biggest concern is our user experience. We want to have these videos with the overlays available for them as soon as possible.
All right, we have a couple more questions coming in.
I need to refresh
this. Yeah, what monitoring tools are you using for model monitoring?
We use humans. So we have a team of annotators. They look at our annotations and give us feedback, not only just on the annotation quality, but they give us other metadata about this video, what time of the day, what kind of road, what kind of condition. So that's how we kind of source our ground truth. It is actually, it's a pretty cool process. Bottleneck equals a slowdown. Not sure if I understand this correctly, but if you're referring to whether we have like difficulties deploying our models, we don't. Kubernetes deployment works pretty well for us. Sorry, I'm not sure if I understood the question. If you can just maybe elaborate more, I can try to answer it. What kind of infrastructure need to have for processing these videos? It is on-prem or some cloud provider. So we have basically this. This is a simplified version. We have a few more pieces to this, but this is deployed on Kubernetes on our AWS infrastructure. So this itself is a Kubernetes cluster. And you can imagine this is our maybe production environment. We have a copy of this in our staging environment, a different cluster, and then a preview environment in a different cluster. But everything is on AWS for us. Can you please explain how you keep improving the models and keep deploying without any delay? How we improve the models will be a question for our researchers. I do not improve the models. Basically, we just deploy a new version of the model. Kubernetes handle those like rolling deployment for us, so there should be no delay. Essentially, they would train a model and save the model artifact locally, upload that to S3 bucket, and our Kubernetes deployment refer to that different model path. Tools like Prometheus or ELK. We use Datadog here, but it shouldn't really matter which one you choose. They should probably mostly have like the similar functionalities. All right, let me just go back and see if I missed anything.
Yeah, anything else from the audience?
Are you guys looking to adopt ML ops practices in KT? What specific ML ops practices? I guess a lot of the things I talked about today can be categorized as ML ops. How are you managing? Yeah, maybe you can tell me a little more about specific parts of ML ops that you're interested in, and I can tell you what we do here. How are you managing the features when model is being retrained due to drift? Not sure. I have no idea. Good question for our researchers. I can get back to you. Major issue that you have to face when deploy. Okay, got it. I think scaling was a pretty big issue for us. We thought that we can use some of the Kubernetes out of the box scaling strategy, which did not work for us. But luckily, this Cron schedule thing is working for now. But we potentially, if our traffic gets a lot less predictable in the future, or if we start selling our dash cams more and more, scaling those, even though it's we still have to like manually go into the dashboard and check the traffic pattern and calculate these numbers every now and then. So this could also get a lot more complicated if the pattern changes too frequently. So that's something that maybe we have to revisit in the future. So I would say that's probably one of our biggest issues. Feature store. I think we don't really have a feature store because this is like a computer vision model. So we just have like raw videos as the input. We don't really have like features per se.
Very cool. Question for you, Tina. Do you identify more as a ML researcher or someone who operates and works on Kubernetes?
I was a data scientist before I joined KeepTruckin. So I built models for about 2 years, but that's when I learned how hard it is to actually put your model into production without the help of a strong platform team. And that's why I joined KT. So I think now I don't know what I identify with the most. Yeah, not sure. I guess
Good answer.
Ex data scientist, but now ML platform person.
Good answer. Yeah, I would say based on your question to the audience, there's quite a lot of twos, and then there's maybe a couple ones as well.
Oh, nice. Thank you. Thank you for that.
All right, any final questions from the audience? Oh, there's one.
Someone seeking a job as ML engineer at KT, can you guide what skills and experience one has to have? Well, thank you for your interest. Personally, I did not know like most of the stuff that I talked about today when I joined KT. I think that's one thing I really appreciate about my company is we do hire for potential. So I think they saw something in me that I didn't know, didn't see in myself. But I think exposure to container, Kubernetes would be pretty important. Mostly day to day we use Python. I guess our team specifically, we also have like the data engineering part of things. So sometimes when you're on call, we also help out with the ETL, job debugging, data warehouse, and we use Snowflake. I guess these are the things that you can probably learn after you join us, but just a heads up that you'll also maybe work on some of the data pipelines stuff. But I think, yeah, if you're interested, you think what we do is cool, it's meaningful, you can hit me up after this. We can chat more. Oh, I forgot to put my, sorry, let me reshare again so that I can show my contact information here. Have you tried any tool other than Kubernetes for managing all the deployment options? I'm not sure. When I joined KT about a year and a half ago, we already have everything on Kubernetes. I guess another cool thing, if you want to join us, is we do use a lot of pretty cutting edge technologies here.
Well, any questions for either Ashley or Tina from the audience? Oh, we have one more.
Do I miss my data science days now that I'm working as an ML engineer? One thing I miss is kind of being closer to the customer and the business. When I was looking at the data, I kind of understand what my company does a lot more and where our customers are from, what industries they are in. What I don't miss is reading a lot of papers. But now as an engineer working more on the platform side, sometimes my day-to-day, I don't really think about how this platform improvement really affect our end customers, but more how this affects our internal customers, which are our researchers, our data scientists. So that's something I miss, especially working from home. It's harder to kind of feel like you're in a company with many teams and understand your customers. That's something I miss from creating models and analyzing data. Do I use data science? I do not. No, I don't anymore. I don't build models anymore. Maybe one day. What is the open source framework you're using for model training, such as TensorFlow, PyTorch? I think most of models are trained in TensorFlow, if not all of them. And we train them on KeepFlow.
Very cool.
Any last words from Ashley about the hiring side of things?
Only that if you are interested in any of our roles at KeepTruckin, you can find everything at keeptruckin.com/careers. And you can also follow us on LinkedIn, and you should get pinged when any new roles open that way. And thanks, Tina, for a great presentation.
Thank you, Ashley. Just one more question about PyTorch with TensorFlow serving. If I remember correctly, PyTorch does not work with TensorFlow serving. There's something else called Onyx. Maybe I'm pronouncing it wrong. ONNX. But I don't know anything about that framework. Maybe you can do some research more on that. But I think it doesn't work with PyTorch.
Cool. Tina, is there a way to reach you that you want to drop in the Slack in case people have follow-up questions?
Sure. Let me put in my email. And I'm always looking for more Instagram friends, so you can find me there.
Awesome. Well, thank you so much for your presentation. Thank you for, sharing about your career as well and answering all these questions. Tina shared her Instagram and her email in the chat if you have follow-up questions for her. This video will be posted on YouTube as well. And if you have any questions for me about Women Who Code, I'm going to drop the link to join the Women Who Code Cloud community in the chat as well. Yeah, thank you everyone for spending some time with us.
Thank you. Bye-bye.
Yes, the recording will be posted on YouTube.
Thanks, Yui.
Thank you, everyone.